Hello everyone, welcome back to another video. So today we are going to discuss the editorial for Codeforces round 998 due 3, and as you can see I was able to solve first 5 problems. So we'll discuss only first 5 problems. I tried if I found it was based on some mathematics and PhD. I tried it for some time but I was unable to solve. And talking about my rank is around 900, I think. Yeah, and I made some uh, stupid mistakes on B and C. That's why my rank is so bad, due to those two penalties of each penalty of 10 minutes. So this would have been 135 if there were no penalties. Let's just start with the first problem. So in first problem, what we are given is four integers a1, a2, a4, a5, and we need to basically set some value a3 to any positive integer or negative integer or 0, such that uh, in the subsequence in the array created by these numbers, so a1, a2, a3, a4, a5, there are maximum numbers of Fibonacciness. Now Fibonacciness is nothing but number of indices where ai plus 2 is ai plus ai plus 1. So current element is sum of its previous and sum of its previous two elements. So what we have given is a1, a2, a3, a4 and a5. This four integers are given. We have to basically choose some value here such that the Fibonacciness is maximum. So what Fibonacciness is, if we set something with a3, a3 equal to a2 plus a1, similarly a4 equal to a2 plus a3, and a5 equal to a4 plus a3. So these conditions, not all, but if this count of these conditions which are satisfying its maximum. For example, in first case, so 1 we are given is 1 1. This is we have to fill, and this is 3 5. Now if we fill this with 2, so array would become 1 1 2 3 5. Now 2 is equal to its sum of previous two indices. So this is one index. This is equal to previous sum of its previous two elements. Similarly, this is equal to this. So these three indices contributes to Fibonacciness, and our answer comes out to be 3 because there are three indices which satisfies the condition. So we basically need to print what is maximum count of those indices, which can be achieved by replacing this value of a3 with any of the number. Now this is a question of div 3 and constraints are very low, so obvious solution would be a brute force. Now a1, a2 and a4, a5 have values 1 to 100. So what are the possible values of a3? Now possible values of a3 can be, maximum can be 200, because this and this can be 100. Now similarly, what would be the minimum value? Minimum value, we can take it as minus 200, because let's say it has to satisfy this condition. Not even it would be minus 200, but let's just take it as our window. So total 400 options we have, and test cases are 500. So 400 into, let's say, to check each to check Fibonacci series of array, we have to iterate over array. Let's say it is 5, and let's say and the test cases are 500. So this comes out to be 10 to the power 4 into 100, which is 10 to the power 6, which will easily pass. So this is the most brute force solution. Now more optimized solution is to make A3 equal to at least one of the Fibonacci's, because if it is not uh, matching with any of the one, then it matches with 0, so there is no point of checking those options. So to make at least one index which satisfies condition, what are possible values of A3? First is A3 is equal to A1 plus A2 itself. Second is A2 plus A3 equal to A4, that means A3 is A4 minus A2. And third is A3 plus A4 equal to A5. So A3 is A5 and A4. So these are the three options which we need to check. So this is a off one type of solution. So we have basically three options. We check only those three options, find maximum answer, and print it. So this is the solution which I wrote. So first, basically, I created the options vector. So one option is A plus B, second is C minus B, and third is D minus C. Just change the A1, A2 type of representation with A, B, C, D. And then what I'm doing is I'm creating that vector by replacing the third element with options of I, and then basically calculating the number of uh, indices where this condition is satisfied and taking its max with my answer. So this was the first problem, pretty easy brute force solution. This one was a little bit tricky. So we are given n cows. So farmer John's and cows are playing card game, and farmer John has n into m cards numbered from 0 to n into m minus 1. Now he distributes m cards to each of his n cows. Now farmer John wants the game to be fair, so cows should be able to play one card per round, and he decides to determine a turn order. Now turn order is nothing but a permutation. So let's call its permutation as P. So in one round, in first turn, P1th cow plays the uh, puts the card on the top of center pile. Then P second, whatever element was there on second index of our permutation. This goes to up till one round. Now in next round again, same order is followed until m rounds are played. Yeah, until m rounds are played. So but only catch here is that uh, whenever you place a card on top of the center pile, the card must be greater than the number which is at the top right now. So whenever you place a card, you are allowed to place a card if and only if the top of the card is top of deck of current card on which is on top of deck, it must be smaller than the card which you are going to replace. And basically we need to fix that permutation, find that permutation, and if there is no such permutation, we print -1. So let's take this example 2 3, and 1, 5, and 3. Now here, one of the possible, the only possible solution is this permutation. So this is the order in which cows must play. So first, uh, on first turn, on first turn, cow one should play. So cow one places 0 on top. So this is the, let's say this is the stack or stack of cards. So previous card is -1, then cow 1 places 0, then cow 2 places 1, then cow 3 places 2, cow 1 places 2, then cow 2 places 3, and then 4, 5 is placed. So this condition is satisfied using this permutation. So we have to print that permutation. So in this permutation, it's I think in no in one base indexing. So 1 2 is the answer here. For n equal to n and m equal to 1, so there is just one answer, which is 1. Now this is the third case for, I will show you this one because it is of -1 condition. Now order is order here can only be 2 1, because if you take 1 2 as order, we already know that this cannot be placed first because 0 cannot be placed after 1. So this possible, this is not a possible permutation. Only possible permutation is 2 1 for at least first round. So first 0 is placed. Now first cow will place 1. Now again second cow needs to place a card on top of deck. Now only option cow has is 3. So 3 is placed on top of that deck. Now first cow needs to place 2. Now this our condition here fails because 2 cannot be placed on a greater number. It always needs to be placed on smaller number. So this fails, and there are no other possible permutations. So answer here is -1. Now what observation which you can make here is that the stack will always look something like this. And in each cow, let's say cow I, will always place the cards in increasing order. So let's say cow has something like 491 cards. In first round of that cow, in first round of that play, that cow will always place the minimum element, then its next minimum, then its next. So always in ascending order, because if it is not in ascending order, there would be some card which would be, if let's say cow places 9 first, then there would be some card later which would be less than 9. So our condition will fail. So cow always places uh, cards uh, which it has in an increasing order. So let's say these are the cards now. Now according to first round, we can fix we have to fix the permutation. We have to use this arrangement itself. So if first round has order like 0 1 2, now our permutation is fixed, that we always need to use follow this permutation itself. So something, let's say there was uh, this type of arrangement in our first round of play. So first cow would have to play first, then second, and then zeroth cow. So based on the first column, we have our possible permutation. Now after we find possible permutation, what we need to do is we need to just check if this permutation is satisfied by all other rounds. This is the main logic of the question. So I will just explain code so it will be better. So first of all, taking that vector input, 2D vector input, and then what I'm doing is I'm sorting all the vectors. Now what I have done is based on first column, I have generated a target vector of pairs where I'm storing a of j of 0, that is the card number and its index. Then what I'm doing is I'm sorting it. Now second element of the target variable will store the index. So basically we will have a permutation based on the second element in that vector pair. Now for each column I am generating similar variable, similar structure like target with current. Then I am sorting that current. Now as the permutation found with target, the same permutation there should be the same permutation with current. If it is not matching, I will just return -1. There is also an additional condition that the elements which I'm first putting with target, so first column elements, whatever there was max. So let's say if the first column was like something like 0, 1, 3. Now there was 0, 2, 4, and 5. So stack would look like 0, 1, 3 because first round. Then I have to put again 2, which is false because this condition here, the condition failed. So what I need to check is whatever the first element was of current is should be greater than the last element of our target variable. If it is not, I'm printing again -1 and updating target with current. So to check this condition again for next time, I have to keep updating target. Now the information is not lost of that permutation because if the code is coming till here, that means both have same permutation. And finally, if none of the conditions satisfy, we are just printing that permutation here. This might be a more difficult solution. I think ideal solution would be something like we just need to check if everything has a configuration like this 0, 1, 2, then there should be 3, 4, 5, 6, 7, 9, 10, 11, 12, something like this. So we first sort all the vectors and then we start from we also sort these vectors according to first element. Then we start from this element and go iterate column wise. So while iterating, each value should increment by 1. So something, so 0, 1, 2, 3, 4, 5, 6, 7, 9. This type of condition should satisfy. So this would be a simpler solution. Just check if it has this type of configuration. What I did might be overkill for this problem, but anything would work, as this solution came to my mind first. Now moving to third. So this is much more easier than B, definitely. So what this in this question we are given that Alice and Bob are playing game, and there are n integers written on blackboard, and n is even. Now what we need to do is, we are also given k, another integer k, and there are n by 2 rounds. And in each round, Alice chooses an integer, erases it, and again Bob chooses an integer, erases it. Now if a plus b, so integer chosen by Alice is a, and integer chosen by Bob is b. So if the sum of two elements is equal to k, then we add 1 to our score. Now Alice is playing to minimize the score, and Bob is playing to maximize the score. Now what we need to do is, assuming that both players are playing optimally, what will be the score after the game ends? So let me show you one example. So 4 and 4, n is 4, k is 4, and this is our uh, integer array. So let's say Alice chooses 1 as, in first round, Alice chooses 1. Now Bob chooses 3. So here 1 plus 3 would be equal to k, as it is equal to 4. So our score becomes plus 1. In second round, again Alice chooses 2, then Bob chooses 2, then it becomes k, and answer becomes 1. Answer score gets incremented by 1, and total score is 2. So answer here is 2. Now there can be another configuration in where in first round Alice chooses 2. Then Bob will choose 2. Then answer becomes 4. Score increases, and second round Alice can choose either 3 or 1. Remaining would be 1. Remaining element would always satisfy the sum with k, and score becomes 2. So score cannot go below 2. It will always be 2. Now main observation here is that, first observation, so let's say Alice chooses integer a. Now if there exists a integer b such that it is equal to k minus a, our score gets to plus 1. So if there is this possibility, Bob will always choose this element where there is this where this condition is satisfied. Now let's say Alice chooses integer a, but there is no such element b in the array such that it is equal to k minus a. So b does not exist in the array. So in that case, Bob will choose such an element which does not contribute to our score. The score. That is, let me try to explain it with one example. Let's just take k as 10 and n is 6, and there are elements 1, 9, 2, 8, and 3, 3. Now you can clearly see that 1 and 9 contributes to 10, Similarly, 2 and 8 also contributes to 10, but 3 and 3 does not contribute to 10. So this can be a different set. This can be keep it. We can say this is a different non-contributing set, and this is a contributing set. Now, so whenever Alice chooses an element from non-contributing set, Bob will always choose an element from non-contributing set because it won't harm its score. Because if we choose an uh, element from its contributing set, there would be a paired element here, which would which will not find its counterpart pair counterpart element, and its score would decrease from the maximum score. So it would basically not give maximum score. So if Alice chooses an element from non-contributing set, Bob will also choose from non-contributing set. Now if Alice chooses an element from contributing set, Bob will always choose that element. Always choose its counterpart in that contributing set. So basically what we need to find is we need to find number of pairs such that ai plus bi equal to k, and once we consider them as pair they are removed from set. So in a way, distinct pairs or non-overlapping pairs, and we need them to be count of those pairs should be maximum. So how can we do that is we can create a frequency map. So frequency map, and then iterate over all the unique integers of that frequency map. Now let's say current element which we are iterating is c. Now its counterpart would be k minus c. Now if there are 3 elements of c and there are 5 elements of k minus c, so this is just frequency of 2 elements, our answer would just increase by minimum of 2 elements. So if there are 3 elements and there are 5 elements of this, only 3 of these will be satisfied, and other 2 uh, parts will come in non-contributing set. That means they would be useless. So this is the condition where c is not equal to k minus c. That means both the elements are unequal. Now let's say c and k minus c that equal. That means c is basically k by 2. So there would be single frequency of single element. Let's say that frequency is 9 or x basically. Then our score would increase by x by 2. That is, if there were 8 elements, we can create 4 pairs basically. If there were 9, we still only will be able to create 4 pairs, because additional one would go to that non-contributing or useless set. So this is the main solution. Basically, we need to find the distinct pairs. Now, using this map, there can be another solution with 2 pointers, but this one I was able to understand quickly. So first of all, taking inputs, then I'm storing the creating the frequency map. Now iterating over the map, I'm finding its counterpart, so k minus c dot first. Now if the current element and its counter both are equal, that means C, the current element is equal to k by 2. Then what I'm doing is I'm just adding its frequency. Now if it is odd, I'm subtracting it with minus. I'm decrementing the answer variable, and else I'm just adding minimum of c dot second and mp of d. Now why am I adding the whole frequency instead of divide by 2? Because this condition where I'd have c and k minus c, this will 3 will be added once we are at c, and again 3 will be added when we are at k minus c. So for all other condition we basically have to do divide by 2 uh, in the final result. So to have that generalization, I'm just adding c dot second. So finally when I'm doing divide by 2, so I do it on the whole answer itself. And this is, we need to subtract it at this position itself. You might thought that if 9 and we divide it later 9 by 2, it would eventually come out to be 4. But if this is 9 and someone else is also giving me an odd frequency, which would come out to be 8, and the answer would change. Instead of 9 by 2, 9 by 2, 8, the answer would be 9. So, which is wrong. And finally, I need to print answer by 2. Now this is an additional logic which I did, but this is not necessary because n is even and m will always be even. So non-contributing useless elements would also be even. What I thought here was if the useless elements are odd, then one of the element from contributing set will become useless. So let's say there were three elements in what we can say, there were three elements in useless set and there were six elements. Now this is where n is odd. Let's just take that condition. So there is 1 2 3. Now when Alice chooses this element, Bob chooses this. Now when Alice chooses this, Bob has to choose one of the element from this six elements, which will break one pair's score, which will break one pair, and so that our score decreases by one. So to check that condition, I did that this logic, but this would be never the case because n is always even. So this was the third problem. Now fourth one. Now in fourth one, what we are given is a sequence, and what we are given a operation which we can do, that is we choose an index I and subtract minimum of a of I and a of I plus 1 from both ai plus 1, and basically need to make we need to check if it is possible to make the array non-decreasing. So let's just take this example, 4 5 2 3. So we have to make this non-decreasing. So let's we can perform the operation on this index. So basically minimum of 4 and 5 would be subtracted from these two elements. So 0 1 2 3. Now this array becomes non-decreasing, and so an answer is yes. So if it is not possible, something like 4, 3, 2, 1, if on this array, it would be not possible, because let's perform this operation on this. Now we cannot do anything about this decrease. So we have to print my no. Now here the first and main observation is that we basically need to perform operations from left to right, because while going left to right, the value basically decreases, and whatever value we have on the left, if it is minimum, then only our possibility of the array being increasing or non-decreasing increases. This is the first observation, and this observation is basically enough to solve the problem. We just need to, what we need to do is simulate from left to right. Now you might say that if there is an increasing pair like 4 5, why would why would we decrease this, why would we perform this operation? Now performing operation is always optimal, because the value basically decreases. More the value decrease, the more there are chances that array becomes non increasing. Now second observation is we only need to perform one operation on each pair. Now why is that? Let's say this is x and y, and x is minimum of x and y. So after one operation, it would come out to be y minus x. Now, even if you perform infinite number of operations here, the pair would look like this always, because minimum of this is 0, and subtracting 0 from both the elements will the both elements will remain same always. So only one operation is needed to on each pair is needed, and after that there are no changes. So these are basically two observations. From left to right, go from left to right, perform all the operations, and finally check if the array is sorted or not, and perform only one operation. That is the logic of this question. So from I1 to n, I'm taking minimum of a of I and a of I minus 1, then subtracting that mn from both the elements, and just checking here if a of I minus 1 is greater than ai, because there are no scope of improvement on a of I minus 1. Means we are not performing any operation on minus 1 index from now. So just check if it is greater than a of I, that means the array is not sorted, and if it is, then we just print no, and if none of these conditions are satisfied, then our array is sorted, and we just print yes. So this was the fourth problem. Now in fourth problem itself, I think this is there are many these type of questions. What I have observed is the order in which we perform operation. It would be constant. Either it would be from left to right, and either else it would be from right to left. And the number of operations which you perform are limited. Limited means they are under uh, they are such limited that the complexity is not of n square order. So either there would be log n complexity, or there would be of 1. So always try to follow this type of behavior. Now second type of variation is you do it till some index from left to right, and do it till some index from left to right to left. So in these cases, what we do is we store the information which is done from left to right in a prefix array, and we store from the information from right to right in an suffix array, and basically then iterate over each case where you do prefix operation till index 1, and all in the index are done from right to left. Then we check if we do till index 2 from left to right and all other from right to left, then index 3. So this check is done based on these two pre-computations, and these are O of 1. So n, basically complexity is n or n log n. Which operation you do is dependent on that. So these are only two variations in these types of questions. Either go left to right completely, either go right to left completely. Also, the number of operations which you are performing are limited. Either they are of log n complexity or O of 1. And if this is not the solution, then there would be a solution where at till certain index they are left to right and all other indices are right to left. So that can be solved using this type of pre-computation, so prefix and suffix. So these are the only two variations which I have seen in these types of questions in this difficulty range. Now let's just move to the E problem, graph composition. So in this we are basically given two undirected graphs F and G. F has M1 edges and G has M2 edges, and we can perform operation of on graph F. So what we can do is we can remove an edge which is existing and also add an edge to two vertices in F only, not G. Now what we need to do is we need to perform minimum number of operations such that if there is a path in all the integers u and v such that u and v are from 1 to n, if there is a path in G, there should be also a path in F. So using these operations, if there is a path in G, there should be a path in F. And if so, F should copy the properties of G of connectivity. So if U and V, if there is a path in U and V in F, then it should be there in G also. Let's try to understand with it with an example. So in first case, n is the m1 is 2 and m2 is 1. Now this is an F graph and this is G. F graph is something like 1 2 and 2 3, and G graph is like there is an edge between 1 3 and 2 is separate. Now what we need to do is, first of all, there is a path between 1 and 3, so we need to add a path in 1 and 3. So this path is added, so we did one operation. Now 1 and 2 there is a path, but in G there is no path, so this edge should be removed. So our graph becomes 1 3 2, and this edge is just removed, so we performed another operation. Similarly, there should be no path between 2 and 3 because there is no path between G 2 and 3 in G graph, so we remove it again. So 1 3 and this is 2, so plus 1. So what we did was three number of operations, and our answer is 3. So this is what we have to do. We have to either add or remove edges such that this condition is satisfied. That is, if there is a path between u and v in G, there should be a path in F for u and v. Similarly, if there is not a path in u and v in G, there should be no path in F as well. So F should copy properties of G in perspective of connectivity. Now, the first misconception of this problem is that the graph should be equal to G itself. That means all the edges of F should be equal to edges of G. This is not correct. No, this is correct. This will satisfy all our conditions, but this has to be always true. That is false, because this can be an F graph and this can be a G graph. Now, here edges are 1, 2, 2 and 1, 2, 3. Here edges are 1, 2, 2 and 2, 2, 3. So there is a difference between these edges, but still we can go from 2 to 3, 2 to 1, 1 to 2, 1 to 3, 3 to 1, 3 to 2 in this graph also. So connectivity is equivalent, but edges are not equal. So this is the first misconception, that we need to make all edges of F equal to G. This is not true. Now, whenever there is something related to connectivity, we always work with connected components. Now, what connected components are? So, this is the graph. This is a singular graph with multiple connected components. So, each component, this block is called as component. Now, what are conditions of component? That from each node to any other node in that component, it should there should be a path. Now 1 to 3 there is a path, but 1 to 5 we cannot go. That's why both of them are in different components. So why we are using it? That for both F and G, we need to make sure that these components are equal. Now why is that? Let's say there is a component with element 1, 2, 3, but here only component the component structure is something like this. 1 or 2 are in a component and 3 is different. Now in this case, what we need to do is we need to make 3 separate from all other components. That is, we need to remove the edge between 3 to any other element in that component. So this type of operation is removal operation. Now when we are performing removal, when the 3 is not in component with 2 and 1, so all the edges will be removed. Now how can we perform that? So first of all, what we are doing is we are iterating over G. So this was the, let's say this was the G graph. In first case, yeah, so this was the first graph. Now we are iterating over it and marking component for each of the vertices. Now 1, 3 is first component, so we are marking it with 1. Each vertex is with 1. 2 is second component, so we are marking it with 2. Now all the edges in F, in F, if component of U is not equal to component of V in G. That means we found this component, marked them, and we have stored in it in vector component. So if there is an edge between 1 and 2 in F, that is component 1, component 2 in perspective of G, then what we need to do is we need to remove that edge, the current edge of U and V. We need to remove this. So basically increment our total number of operations. Now this takes care of all the removal operations. Now add what we need to add, which edges which we need to add. Now after removing, there would be multiple separate components here. So there would be 1 2 3 4 and 5 6. But in our G, one, let's say 1 2 3 4 was a single component and 5 6 was single component. Now what we need to do is we need to basically make them connected, these two components. Now how can we do that? We just need to add one edge between any of the nodes and it would become connected. Now how can we do that is we basically iterate over components of F after removing these edges. So after when we remove this edge, we create another graph. So which is, let's call it F dash, which is after removing the required removal edges, we create this graph. Now we iterate over each component and mark its any of its vertices according to G's value. So one should accord, let's call it this as component 1, this as component 2. Now first component should belong to component number 1 in G. Similarly, second component, this 3 4 would also needs to belong to component 1 according to G. This component needs to belong to 2. So we basically have a frequency of components. So this ID component has 2 components in F and this ID component has 1. Now whenever there are 2 components, we attach them. So we add age between them. Now let's say there were 3 components of same ID. So this one, this one, this one. What we do is, so there were 3 components and we have to make them connected because they belong to same component in G. So we add 2 edges. So if there were C and T components, we need to add C and T minus 1 edges between them. So this takes care of all the addition of edges operations. So first we took care of removal and then add. Now the components in both F and G would look same and we have minimum number of operations required count as well. So we print that finally. This is the solution for E. So talking about the code, first of all I declared some adjacency matrix. One is for F and one is for G. Now for F, I'm creating this adjacency matrix plus I'm pushing all the edges. I need to store those edges when in the case where I'm removing that. We will see that in code when it is required. Similarly, I'm creating adjacency list for G graph. Now I'm marking components of G graph. For that, I have declared a variable C and T. So how do we do that? Whenever we get a unvisited element. Then what we do is we visit all the elements which are possible from which has a path from that element. And then what I'm doing is I'm just marking their component with C and T. And once all of them are visited, I'm incrementing the counter variable. So we have marked all the components of each element in G graph. Now what I'm doing is I'm iterating over the edges of F, and whenever I found that there is an edge between two elements such that their component is not equal, so we need to remove it. So I'm including the answer variable, and for all the edges which are not removed, I have created and third graph which is adjacency 3. So this F dash graph. Now in F dash graph, I'm basically what I'm doing is I'm finding the number of components again, but this time I am storing the frequency according to G's graph. So this is what I'm doing. So if this was supposed to be component number one, and this component was also supposed to be component number one. So how many uh, components are there? So this frequency one, for ID1 there were two, for ID2 there were one. So I'm basically storing it into this count map, and finally adding that counts minus one variable. So if there are two components, only one edge would be required. If there were three, two edges would be required. If there were four, three edges would be required. And finally printing the answer. So this was fifth problem. I think problems were more difficult and more tricky than usual due threes. Definitely F and G are a lot difficult because there are so less solves for it, both of them. And first five problems were also tricky. From B itself, they were tricky. And I performed, I guess, good. The penalties were expensive, but if there were no penalties, I would have ranked around 700, I think. Overall, good contest. Problems were interesting, and I guess that's it from my side. And if the tutorial was useful, please let me know. And thank you for watching.